Yes, so maybe you can start.
Oh, yeah.
Yeah, so it's my pleasure to. Kyoung-Seog is a research assistant professor here in IMSA. So this institute, in my opinion, will tell us something about singularities.
Yeah, thank you. Thank you very much. So yeah, since I'm the last speaker of this conference, let me thanks to the organizer and the friends for organizing and helping to have this wonderful conference. So let's thanks to the organizer. Okay, thank you. And okay, let me start. So today I'm going to talk about the Hilbert scheme of Markov singularities and lattice factorization. Schemes of singularities. Is it visible from? Okay. Okay, and this is a joint talk based on a joint talk in progress with the book and yourself. Was second speaker. Okay. Okay, we start. So yeah, but this is in quite early stage, so I will be very grateful if you give me any comments or suggestions. Okay, let's start. Let's have the polynomial two variables. So suppose that I have a polynomial from C, and suppose that I have this so and I consider some zero locus this polynomial and it corresponds to C, and suppose that C has an isolated singularity at the origin. The C has an isolated singularity at the origin. And then I consider this small ball from this origin, and then I consider its intersection. So intersection. So I consider this intersection of this C and this C, and this gives me a knot or general link. So let me call. I hope it's algebraic. So for example, when f is xy, and it has an isolated singularity at the origin, and then this string is famous book ring, and when f is x squared plus y cubed, then this gives me the famous trapezoid. So okay, so then there are several topological invariants I can assign to this algebraic ring. So for the Alexander polynomial and also Jones polynomial. Yeah, and there are another topological invariant which generalize both Alexander polynomial and Jones polynomial. So for HOMFLY-PT polynomial, I think everybody knows this much better than I. And yeah, I suppose the HOMFLY-PT polynomial. This PT polynomial. This algebraic ring. Or I mean, for any knot or ring, I can obtain this invariant. So I have this oriented ring, and I obtain this polynomial which lives in this plus minus 1 plus minus 1. And I mean, it satisfies this kind of simulation. Let me not define this, but anyway, I define my HOMFLY polynomial to not to be 1, and then this kind of relation is for HOMFLY polynomial of this the ring. So for example, this top ring. Check that this is negative a q minus q plus q minus a. So if I consider this tripolar, and this is nothing but a scale, q scale plus a scale, q negative 2 minus 8. Okay, so anyway, this is some topological invariant which generalize these two. If I specialize HOMFLY polynomial by looking a is equal to Q1, then this gives me okay, so I mean, yeah, I think everybody knows this much better than I. So then, because my knot or ring comes from this algebraic geometry, it is quite natural to expect that maybe there might be some way to express this HOMFLY polynomial as from certain data of algebraic geometry of this plane called singularity. And indeed, this is the case. So there's a theorem by, so it was originally conjectured by Oblomkov-Shende, and later it was generalized by Kyoung-Seog and Hilbert, and finally it was proved by Maulik. So anyway, let me show the formula. So this HOMFLY polynomial can be expressed as an algebraic geometry form. So this HOMFLY polynomial is nothing but a over q mu. This is Miller form, and 1 minus q scale, and I take integration of the. So I will explain this soon. And then q to the 2l and 1 minus a scale m minus 1 e pi. So I mean, this is purely topological invariant of this now, but I mean they prove that this purely topological invariant can be expressed as in terms of algebraic geometry. Yeah, this way. Let me explain what this means. What this means. So this is, I have this singularity. This is curve, and this zero is my singular point, and then this C shadow L. This L. This is something called a closed subvariety of this Hilbert scheme of points, L scheme or L points on this curve whose closed point parameterized this subscheme of C. Then theoretically supportive. Then theoretically supported on this singular. Theoretically supported singular point. So this is, and this one is nothing but collection of all, collection of all. Let's see. Okay. So is there any question?
Can you just say what is L and M?
This L is, this length of this subscheme. So, this is collection of the subscheme C, whose length is L.
It's a non-negative thing.
Yeah, it's non-negative integer. So, I just wrote this, but this is non-negative integer. And the n is the number of generators. So, I have this is collection of ideas. N is the linear number of generators. So anyway, for any ideal, I can I have this L and N, and so this supply polynomial can be expressed.
So you think if all the ideals with given L and M, and you do the Euler characteristic and multiply it by this?
Yeah, right. So this Hilbert scheme has several application, and anyway, I choose this L and M, and then this gives a vector variety. I take the Euler characteristic and multiply this number and add 4. Then this gives this complex. And you can check that, for example, when this the f is xy, you can check this explanation if this polynomial, and also we can check that when f is x squared plus y cubed, then this gives this. Yeah, thank you for the question. So so this is the case, and as I told you, this implied polynomial can be specialized to this polynomial by putting this a for -1. So I apply this a for -1, then this gives me this. If I just plot this one, then this gives me -2. And this is some prime. And I obtain this polynomial, and this is Alexander the polynomial, and how can I say? So when I specialize when a to be -1, then I obtain this formula, and this was indeed already known by Kyoung-Seog Lee. So in any case, so Alexander polynomial, this implied polynomial can be expressed in terms of algebraic geometry. So that's all right. Okay. And so in both cases, this Hilbert scheme plays a very important role. Okay, and then let me tell you one completely different story. So again, let f your polynomial from the end. So one is to be weighted homogeneous polynomial, and weighted homogeneous polynomial F is divisible if satisfy the following two properties. First, F is nothing but can be expressed this way. Ci 1 to n x j to the e I j. So I mean, this first expression tells me that x is summation of n mono, exactly n mono. And second is okay, this is the and this e I j belongs to non-negative integers. J okay, in any case, I can express f in this summation of n monomials. And the second condition is this matrix E I J is E, whose entries are E I J is multiple. If this is the case, then I will call this weighted homogeneous polynomial to be invertible polynomial. Then, so why I'm saying this one? So because I mean I will discuss mirror symmetry for this singularity and the state to state mirror symmetry for singularity. I will discuss this mirror symmetry for this. Okay, and this invertible polynomial is non-degenerate. If it has an isolated singularity. That's an isolated singularity and theoretical. And if this is the case, so there is a famous construction by Oblomkov-Shende So they claim that so when f is an invertible polynomial, looks like this one next to the E I J, then they define this Oblomkov-Shende transpose of this invertible polynomial in this way. Just simple. So I just this is the same. And I take the same monomial, but now I take transpose. Sorry, transpose. So I mean, if I consider same polynomial, same type of polynomial with the transpose matrix, and this is the Oblomkov-Shende. And there are some group action acting on this case. So let GF be symmetric group of this acting on this and such that F from the one x one, the xm is F. So M. No, this is just a symmetric group, and yeah, and I can define RF. This is so this is a grading group. I is from N G X I from Z F. So this is just the formal variable corresponds to this variable. The F is just polynomial modulo this relation. So this F minus J 1 to n, and as I told you, it's E ij integer. So I from I equal to 1 to n. So then this is abelian group of rank 1. Because I have n variable and the work and so there's one more. So n plus 1 variable. I order this by n relation, so this is rank 1 abelian group. Okay. So then yeah, so I have this abelian group and this G and this single style is the also define I also define this G. So then again let me show this again overlooked. And that for any subgroup of this G F, I can define GT in transpose group to be written from GF to G system. I define this transpose group, and why I'm saying all this, because there is mirror symmetric conjecture by Oblomkov-Shende, saying that this FG is mirror to this FT and GT. So there's mirror symmetry for invertible polynomials. And the Oblomkov-Shende claim that by some physical reasoning, so this FG is mirror to this transpose polynomial with
I just ask you a few things. So this LF it's like an infinite group, or it can be finite? Or?
It's an infinite group, but there are some. I mean, it's basically G plus some finite group. It's rank 1 abelian
So
group.
there is some finite.
Yeah, some finite
stuff.
part.
So when you take like a group algebra, is it CL?
Yeah. So yeah, this is basically this part times some finite. You know, this G is a free I mean, you know, by
So
fundamental zero.
this G hat will be a finite group.
Yeah. G hat is finite. I mean, no. This
So
G hat is not finite group.
What is it?
This should contain this part. That is.
Okay. Oh, yeah, I see.
I still don't understand the explanation. So G hat is C star to the n times a few copies of that, or G star just C star. What's the rank of that?
So yeah, this has rank 1.
Just rank 1.
Rank 1, and there might be some finite group factor, but anyway,
I got it. That's because you talk about knots. You have rank 1. Why is it rank 1? I mean, I missed that. It wasn't very careful. Why rank 1 and not higher?
So I mean, how can I say it? It's just I mean, you know, this is n plus 1 more variable. So this is n variable.
Yeah.
This is one more variable. So rest 4. This is n.
And it will mark out by what?
And then I model this by n relation.
Oh.
Because this invertible polynomial is a summation of the exactly n polynomial. And then for each term, I give this relation. That this is it.
Does this G hat appear anywhere in this mirror symmetry statement?
G hat is kind of sorry, I should also mention.
Well,
So, G hat is preserving this. G hat is preserving this F basically, and I mean G hat is nothing but G hat is sorry, I think I wrote something wrong. So sorry, G G hat is basically preserving. Sorry, this is my G hat. Sorry, this G hat is this group action preserving this polynomial, and the G is G is subgroup. G F is subgroup of G F such that all these terms be one. So all this term to be then I'm sorry. So G hat is basically subgroup of this one, but there is some extra condition. Like if I give some extra condition. Sorry, maybe I right. It's just imposing this. J is 1 for every R. If I impose this condition to this group, then I will recover this G. Okay, well, G hat is anyway this group preserving this map. Thank you. So, yeah. Anyway, this is the so by mirror symmetry conjecture, this G FG is mirror to this the transpose groups, and again,
But it is not like a precise theorem, right? Or is it the theorem now, or
no, I don't think it's just
even just for some cases?
Some cases this is true.
Okay.
But in hot theoretic level, this is proven for many cases by Affiliation.
And on the homology.
And I will discuss this homology covers. Yeah, thank you. Yeah, so this is proved for many cases. I forgot the detail, but hot theory can verify this really gives the
Or maybe is there like a known counter example where it doesn't work?
No, I think the no count.
Okay.
It's really, very, I was, to be honest, very surprised when I first saw this because the mirror is so simply defined.
So,
But yes.
yeah, maybe that. So what Hodge mirror on what?
Sorry, I should say that there are kind of hot structure I think you saw before. So this G is symmetric group.
So that I see some letters there. What O?
So this G is symmetrical this F, and how can I say? So when I have this polynomial, then I can give some kind of grading structure on this this how can I say this there are some way to assign some hot structure here with this symmetry.
To put a Hodge structure, you need the variety, or let's say quasi-projective variety or something.
Right,
So
right.
that's a variety.
Right, but yeah, that's completely true. But no. So in general structure, I just need this complex. I just need this vector space, complex vector spaces, and complex conjugations that is fine.
Okay, so
yeah.
So it's not a Hodge structure on a manifold. It's just
it's some general. It doesn't come from this scalar manifold.
It's a linear algebraic one.
Yeah. So it's
and it's a Hodge, not mixed Hodge.
Yeah, it's not mixed Hodge, but sometimes mixed up structure here. For example, like the one to the space, so there are some mixed Hodge structure.
So you put this Hodge or mixed Hodge structure on one vector space. But what's a vector space?
So yeah, to be honest,
usually
it's a
forgot.
vague. Yeah, it's a little bit too vague for me.
Oh, I see. Yeah. Can I talk to you later? I have some notes explain that. So if you want, I can explain.
Well, I need because of the conference.
Oh, okay.
But it's okay. Go ahead.
Yeah, I see. Yeah. Sorry.
So there's this paper like Hodge structures coming from mirror symmetry or like. So there is this idea that there is this like what we also talk about the equivalence of this category and derived category, and you can assign to these categories these Hodge structures, but those can be these non-abelian Hodge structures. So it's yeah. So yeah, this is also very way just. It can be even something more exotical than the usual mixed structure, right? It can be this.
I mean, part of the reason I'm asking the previous talk, Joseph kind of mentioned that mixed structure was something very concrete on the middle fiber. Right?
Yeah, right.
Now it's more esoteric, so I'm not sure exactly. Is the same mixed structure or is something different? Because the middle fiber, they had bigger embedded numbers, right? Here, it's just.
I should okay. Then how can I say? You know what? One way to.
So are we speaking of kind of branching circles?
Anything I mean, how can I say? In Joseph's talk, I mean, you know, I have this polynomial with isolated singularities, and if I have some middle fiber here, then you know, if I have P and P, if I have middle fiber, then the simply I think prove that there is the mixed structure in this homology of this middle fiber. Then, I mean, what Joseph did is there is a monodromy this monodromy here, and so I consider the same thing to part of this monodromy, and so this happens. This mixed structure is quite compatible with this, and this spectrum there was the eigenvalue of this semi-simple part of the action, semi-simple action. So the action of semi-simple part of this monodromy. In this case, it's someone. To be honest, I should be a little careful that. So vector space level, I think the dimension of vector space here and there are the same. But to be honest, I haven't checked that. I said. Yeah, for some cases, I mean, because I now have this G action here, so there are some extra complication. But if G is trivial, then I think the mixed structure there is the same. And if there is, I mean, because I have the extra G action, I need to go a little careful to the spectrum.
But anyhow, this helps. Thank you.
Yeah, and then thank you. And then I have this very weighted polynomial, and I just need to consider only this. So only only thinking about eigenvalues. Yeah, in any case, sorry for this. Thank you. So and then, anyway, so this this hot theory level is proven, and in homological mirrorsymmetry, as I said, pointed out, I can consider homological mirrorsymmetry version of this conjecture, and homological mirrorsymmetry was first suggested by Kyoung-Seog, but for this specific level, I think it was. As far as I understand, there was Takashi who conjecture that I will explain both sides. This is there is a homological mirrorsymmetry is nothing but the matrix factorization, category of matrix factorization is equivalent to category of directive. So this is class identity category, and this is the homotopy category of matrix factorization. I will explain this. So anyway, so homological mirrorsymmetry version. I mean, this homological mirrorsymmetry version of this conjecture.
This LF is the same LF.
Yeah, LF is exactly the same. Yeah. So and then what we want to do is to combine these two things. So I mean, as I told you, I have this. So when f is two variable polynomial here, and this is invertible, And there are two stories. One is homological mirror symmetry, and one is HOMFLY polynomial. So I want to combine these two stories. I mean, what we are trying to do is to combine these two stories together and see what's happening. Okay, so in order to do that, we let's say explain what this guy is. So let us be the polynomial or sometimes one of series or model of series. And this RF action, RF is a natural action here. Then I consider also, and then this has natural grading with respect to this RF. And the left M is RF again graded as module. Then yeah, this means that I can. Then there's natural shifting action here. So and arrow R5 where this one is not. Okay, so there's I consider this RF grading as modules, and then these modules category of the grading module has a natural shifting operator. Shifting this. Okay, so then this RF grading matrix factorization, category of grading matrix factorization. Of F is nothing but this pair of two these are two RF grading three S modules of finite rank, and I have a map from here to here F0 and here F1, and so the matrix factorization of F means that if I compose this map and this map, and this is F, F0, F1, F times identity of this matrix, and the F1 composition F0, this is again F. If this composition is F times identity and this composition is F times identity, then I will call this to be RF grading matrix factorization. Okay, then you can again define a natural homomorphism between this grading matrix factorization, and also we can consider all the category of this matrix factorization. So this gives this category. And here, this is balancing cycle. And object is balancing cycle there. And this is so following is
20.
20. Okay. So I introduce these players and. So anyway, I have this matrix factorization. So then let's consider this Hilbert scheme. So, and because there is action here, so I mean I can find this action here. There is G and action here, which is nothing but this C. Okay, and then I consider some ideas here, which is invariant in respect to this one. This one, and I apply here. And this, if there is something, if the show multiply of this group is trivial, then I can assign an equivalent structure here. So if I have the element here, then this is an object in this RF module, which is RF gradient. So this RF is now involved in X1, and here's again this RF gradient. So in any case, this ideal is this module, and then this ideal, because this is module, I can consider the derived category, because this belongs to here, this also belongs to the derived category of RF graded RF modules. And then there's a map from here to for the triangulated category of singularity. Right, this way. So this is nothing but this one quotient of this category by perfect complex. So anyway, there's natural function from here to here, and by a famous theorem of Oblomkov and Hilbert, there is natural equivalence. And saying that this auto category of matrix factorization is equivalent to this graded matrix factorization category of matrix factorization. Okay. So I mean,
so I is like the equivalent or invariant shape with respect to this action.
yeah. This is the equivalent shape with respect to this section, and this is equivalent to consider RF graded RF module. And the RF is extreme and natural graded structure. Okay, so yeah, and this is So I mean, what I mean is that if I have an ideal which is equivalent to this group, and if show multiplier of this is trivial, then I can naturally give some equivalent structure on this ideal, and this gives some element in this by this function. I can give a natural element here. Okay, there's this combined with two here. Okay, and then as you said, so this homological mirror symmetry conjecture. It was proved for many cases of theorem by really many people. So there are really many people working the question doesn't work. Just go down. How one speaks, show, there are really many words in this section, and in any case, for at least for top case, this is true. Yeah, this factorization is equivalent to this, quasi category.
Okay, so it's hard to work with how that.
Yeah, higher dimension case essentially I think but as I haven't checked maybe this paper carefully. For both top case, Hoffman and Hoffman Smith and George and Chong, they prove this for in general. Okay, anyway, yeah, now we have this thesis theorem. And how they prove this, how I mean, let me explain the general structure. How they prove this theorem. So they prove that indeed, how can I say? Of course, there are several ways to prove this one. But I mean, the most, popular way is to construct a certain exceptional collection on both sides and compare this exception this structure behind this exceptional collection. So let me explain what this exceptional collection is. Let T be a triangulated ring, and the definition of the exceptional object E is, an object E in T is exceptional. If form E and E shifted by some number is C if K is zero. If I do not shift anything, then there's natural identity map. So this is only and zero if K. So an object in T is called exceptional. Okay, and the sequence of exceptional objects and this is a or exceptional object is called exceptional collection. Exceptional collection if there is no home between from back to forth. If home from EI to EJ shifted by K is trivial for any I greater than J. And why this exceptional collection play an important role? Yeah. So because when I have an exceptional collection, it is that there's notion of strong exceptional collection. Strong if this exceptional collection is strong if home from EI to EJ, K is zero when K is okay, anyway, there is notion of strong exceptional collection. Anyway, if I have this strong exceptional collection, then there's a theorem by Honda.
So there is no conditional I and J in strong.
Yeah, strong exceptional collection. So exceptional means there's no home from back to forth.
Yeah.
And the strong means that there might be home from front to back. But if I shift, then there's no home. So for example, if I have Kn, and this O1, and this is famous balancing sequence. This is a strong exceptional collection because there can be home from here to here, but if I shift, there's no home.
I'm a little confused because it seems to me that the strong condition is less strong than the.
No. I mean, if I have an exceptional collection, then this exceptional collection is strong if it satisfies this addition.
So there is still this condition that
Yeah.
if I is bigger than J, then there is no home.
Right.
Okay.
Right. Sorry, I should. That is E1. And already exceptional collection.
Oh, I see.
Yeah. So anyway, why I'm saying this? Because suppose that I have my triangular category is generated by this exceptional connection, and suppose that this is strong. Then this there's a theorem by Honda that this can be identified as a keyboard representation. There's something keyboard keyboard representations of certain keyboard exists. There's some relation. There's some keyboard with a relation, and I can consider some. Anyway, there's some ring such that some ring, some keyboard, and I can express this triangle category as a derived keyboard representation.
This is I, so it's some ideal.
There are some relations. For example, yeah, I mean there might be some, an arrow here, and yeah. So what I'm saying is because the most, one of the ways to prove this one is that I slightly perturb this class identity category to make this into a bunch of balancing cycles. And then I can, cite that I could describe some way to compute morphism from here. So anyway, there's natural exceptional collection from this on the symplectic geometry side. And if I can construct some so-called exceptional collection here, then this gives this identification. And moreover, from this exceptional collection, I can compare this and this via certain keyboard representation.
So you more simplify the function.
Yeah. I slightly perturb this function to make this into most function, and then
It doesn't change the topic.
yeah, right. So yeah, that's the okay. So anyway, because of that, really many people study the exceptional collection here, right? Because that's one way to prove symmetry. So really many people try to construct exceptional collection here. So again, I should write many things. Sorry, this title. Maybe now, but in any case, they prove that this factorization category has full exceptional collection, and indeed prove that when n is greater than or equal to 3, this is indeed strong. There are strong exceptions. There are really many results. N is the dimension of this F is En plus D. It has an n variable. N is the number of variables.
So it also
curve singularity, surface singularity, surface singularity, up to surface singularity. This has a exception.
And there are
strong exception.
Is it known that there are no strong for some higher than
higher? I think it's a condition by Orlo. Say that for any case there might be strong exceptional collection. There will be strong. I think that's a condition of Orlo. Anyway, he proved this until those three. Anyway, in this case, it can be about this. Okay, so then now, so anyway, we have many exceptional collections here. Let me write down the theorem. Okay, so anyway, indeed, yeah, there are lots of works in this studying this category because it is one of the player symmetry. So there is again so-called standard condition constructed in this category, and also it has strong exceptional connection, and also we can study so-called Bosland right and keyboard like this. So there are lots of works in construction. Okay, and let me write it as a conjecture or maybe question. then okay, I have this invertible polynomial, which maps C2 to C, and have an isolated singularity at origin. And then, like claims that there is a stratification on this thing. And as I told you, if I have an ideal here, and this goes to this matrix factorization category, and there's a stability condition here, natural stability condition here. So indeed, the original question we were studying is that can we compare? This stability condition naturally induce certain stability, certain stratification here, and there are several random stratification here. And our original project was to compare the stratification here and here. And okay, so in any case, the question or picture is that there's certain stratification on this Hilbert scheme, which play a important role. This because it is has important role in HOMFLY-PT polynomial. Then there's natural stratification here, such that the original attempt was to compare this stratification here with the stability condition coming from the stability condition and compare it. And such that, in any case, such that the image of elements in Si, if I choose one stratification and choose an element here, is, and I consider image here, then this is of the form I, and there's a grading shape here. So all element here maps to here, and the image should be this form. And we conjecture that this has a nice form. For example, this can be, for example, indecomposable.
So is it this one of the elements of the exceptional collection, or is it just?
Yeah, I already explained. So first we expected this as a nice property. For example, this might be indecomposable, the sense of both standardized and keyword, or this is semi-stable with respect to this stability condition, or we can expect this is exceptional.
So this 1 up to k, those are the different slopes for the.
So each one goes to, each one goes to here, and then this grading shift this page of the step.
Okay, but how does the slope of EI looks for different I?
So then, this depends on this object, the target object.
Oh.
So this might be different, right? So because I expect that this is different.
So maybe what are the, how you get the stratification from the stability condition? How do you get the stratification from the stability condition?
So this Bridgeland stability condition is yeah, that's a good question. So by this Bridgeland stability condition make this triangulated category into certain, for example, divide this triangulated by this hot, and the hot shifted by -1, hot shifted by 1, blah blah blah. And each hot it can be decomposed as some kind of semi-stable object with respect to space theta. So this famous theorem of Adon-Rashman, the Jordan method, tell me each object can be has some kind of iteration by semi-stable object, and each semi-stable object can be also iteration by this stable object, right? This combination of Jordan method and Adon-Rashman, and then anyway, this gives this stratification, right? Because any object can be decomposed in this way, right?
So what is the stratum S1?
But stratum of S1.
What will be one of the stratum? No, I don't get how you decompose this Hilbert scheme.
So I mean, how I can decompose this Hilbert scheme?
Yeah.
So indeed, there's a natural decomposition of this Hilbert scheme.
No, but is it coming from the stability condition?
That's the question.
Oh,
If what we want is to compare stratification coming from this stability condition here. It was our original situation. So coming from stability condition and then compare the natural stability condition. Natural stratification already exists in this Hilbert scheme. We compare whether this is same or not. Okay. Then
I mean, it's 416. So it's a yeah.
Oh, okay, so the theorem I want to tell you that we check this for some cases that the theorem like as I told you, example and step. So anyway, so this is the case. So yeah, this is it is true. When F is of ADE and this is the case, we prove that we can check that this gives an exceptional object here and the shift by something. And indeed, the stratification coming from here and here coincide. That's what we prove. And then, can I spend one more minute? Sorry, so there are natural two directions you can go. So one is we can generalize this vertical case because all the players can be generalized to case. For example, if I have function from C to B to C, then there are many of stories can be generalized in certain case. And second, this is most interesting part. Sorry, I should explain. This gives me another interpretation of this difference between this HOMFLY polynomial minus Alexander polynomial. So by this way, I can reinterpret this difference between HOMFLY and Alexander polynomial in terms of objective matrix factorization, and by mirror symmetry, I can compute this. I can reinterpret the difference between these two invariants as a certain vanishing cycle with the monodromy. Yeah, but we check this only for easy cases, so we hope this to be true for much wider case, but yeah, as I told you, we are in the early stage. Okay, thank you very much.
Do you have any questions? No, I have a question.
Yeah.
So you started with this Maulik's formula, right?
Yeah.
But kind of so you are now like considering some like invariant sheaves.
Yeah.
So is it a problem, or can you like formulate the Maulik's formula just by taking all of these invariant sheaves?
Yeah,
In
this case, it doesn't matter because over the space, the Euler characteristic of this space and this system invariant point are the same.
Oh.
So we don't have to. That's the point in it.
Yeah.
So when this case is all system, and the Euler characteristic of this part and the system invariant are the same. So we don't have to worry. But if F is more general, then I think this might put some problem.
Okay.
That's a good question.
Any other questions? No, then let's go.